Hello everyone, yo wonderful people. You're on Physics with Daniel Dallas. We are on rotational dynamics. Here is one more problem from this topic. I guess it will clarify many positions and answer your questions if you still have them in this area. It's all about the cone rolling uniformly without slipping up, and it's turning around its apex, which is hinged. Okay, so it's hinged and pivoting point. You'll see in a second the problem itself. But before, we're going to go through Euler formula, and also I want to mention that the solution obtained for this problem can be very useful in a similar class of problems when you would like to combine several types of motions, probably translational one with rotational, and you want to see what's the resultant motion, how it looks like, and also you're caring about kinematic parameters of the resultant motion. It's all about that. All right, but before we're gonna go through, I just want to remind you a very interesting formula, Euler formula, that's related to the vector. If it's changed direction, let's say this vector A, and change direction in a space while the value of A stays or remains constant. So let's say over time periods, it changed by the angle delta c theta over time delta t, and now it appears in this way. So obviously it's going to be just another vector, but the magnitude of the vector, let's say, stays the same, so that we can state that let's say A star, maybe it's better. It's not prime, it's not the derivative. A star magnitude or absolute value remains unchanged in that case. So what if we apply derivative to that? So many people think that derivative becomes zero because vector itself magnitude is not changing. So however, it's misleading. So if you want to apply derivative, in that case, you want to find the rate of change of the vector. Just I remind you that vector A is simply A times, magnitude, let's say, times the direction unit vector, let's say I. It's going to be unit vector I along its original position at moment of time t0. So if you differentiate, you actually need to apply the operator of differentiation into i's. In that case, you'll get something like this, right? And as you understand, because the length of the vector is not changing, the magnitude is not changing, however, direction is changing, it leads to obviously omega, because in that case, the vector changing by its position or its direction by the angle delta theta over time delta t. So you're looking for the rate of change of the angle, and that becomes omega. So the Euler formula tells you that in this case, if you apply operator of differentiation to the vector, you'll actually finally get the vector product omega by vector itself. Okay, and if you would like to find the magnitude of the resultant rate of change of the vector, it becomes simply omega times a magnitudes in times sine of the angle, as you remember, according to the vector product. All right, so this formula will be very useful in part B. So I just remind you so that you get all theoretical base for solution for solving this problem. And let's have to go. So here's the problem. Read carefully, try to do by your own, and you'll see my explanation in a few seconds. Alright, so here is the right time to answer the first question about angular velocity. Alright, so the complicated motion of the cone when it's rolling and spinning around point O, which is hinged here, the apex is hinged, can be decomposed into two or more simple motion. So the first one I'll consider as a pure rotation with omega 0 angular velocity, as if there is no rolling of the cone. So it's pure rotation of the cone around OC axis. Okay, So vector omega 0 of angular velocity will be directed in this way according to the screw rule, and we can mark as omega 0. Okay, so this rotation connected with the rotation of the cone around OC axis. So that's about OC axis. Okay. And the second one is simply because your axis OC is turned in a horizontal plane around vertical axis. So we can define another omega 1, which is connected with this sort of rotation of the axis of the cone OC with some linear velocity. Right now we don't know which one. Oh yeah, we know actually. This linear velocity is what we are given. This is velocity v, okay, that we are given, and that's rotation about vertical axis that goes through O. Okay, so and the resultant omega, angular velocity in question, set up in question A, is simply the superposition of omega 0 and omega 1. Okay, and if we represent as the vector, so this vector according to the parallelogram rule can be drawn in this way. So that's omega. But because we need to find omega as a vector at time instance t, so obviously in different times moments due to that component depending on time, so it's turning, right? Because OC is turning every time, so have different directions in different times moment, while omega 1 keeps the same, so this vector connected with OC rotations without rolling, let's say, it keeps the same, so omega will be dependent on time itself as well. So that means we can define the magnitude, and let's say angle theta, that omega as the vector arranged with the vertical axis. So we need to define both magnitude and angle theta. All right, so in which way we can do? So magnitude can be defined as omega 0 squared plus omega 1 squared, and that means we need to define omega 0 and omega 1 as well. Okay, how to work it out? I will start with omega 1 because this is the easiest one. So omega 1 can be defined as linear velocity v, which we're given 3 meters per second, over the radius of rotation. So in this case, it's OC. So that means we need to divide by h. So in different variations, we might be given the radius, we might be given like angle alpha, so we can express those parameters from geometry of the cone. But because we're given height of the cone, so we left as it is. So in our case, it can be 3 meters per second over h. Okay, h is just a parameter. The main question is all about omega 0 because we need to understand omega 0 as the pure rotation of the cone around OC. So around OC, that means we need to define linear velocity of the pure rotation of the cone. So right now we don't know that. I mark R as a rotation, so rotation over the radius, because that's rotation of the cone around OC axis. So that means we need to use the radius of the rotation. So radius of the rotation can be easily expressed through geometry using Pythagoras. So that means radius of the rotation can be expressed as square root of L squared minus H squared. That's from geometry. In the case of if we are given the angle, let's say alpha, we can also express pretty easily. So let's connect R and H. So R over H becomes the tangent of the angle. But this is just in case if you want to see variation of that problem somewhere. That will be very helpful. Okay, so how to define v of the rotation? That's the last case. And that I will move to next slide. Let's consider it separately. So rotation of the cone occurs with the omega angular velocity omega 0, but we need to know linear velocity, which we marked as VR, rotation, VR. How to define, how to connect, because we are only given the velocity of point C. So that were we given only. So here is V of the point C, which is basically sort of translational motion in that case. The answer to that question is pretty obvious. So I'll put one more time, I'll put the formula. So omega 0 around OC is V rotation of the radius. So the main goal is to connect VR with V. How we can do that? If we just put, let's say, we put, let me see, it's right there. Yeah, we can put the circle. So we can use the circle. And let's consider the cone base like that. So here we can draw, we can take this point, no slip up. That means this point at any given time instance is staying on its place. So that means the resultant velocity distribution over time will be like that. So because it's rolling, right? So it's V rotation plus V. Here is just pure V, translational, and resultant of that is a superposition of V for that point and V rotation. So in that case, the resultant, no slipping up, this point stays on its place, so the resultant velocity of rolling and rotation becomes 0. So we can write resultant velocity of that point is simply V minus VR in vector way. And because it stays on its place, no slipping, the resultant is 0. So that means VR becomes translational velocity, however directed in a different way. Okay, so that means we have the final formula for omega 0. And now we can combine. So we've got V over R. Let's go to the previous slide. And let's combine them both. So omega resultant vector becomes simply square root of V over H. But for some, I think because we're given H, I'll leave as it is, V squared over H squared. And on top of that, we need to add V squared over R squared. Okay? So where R is simply L squared minus H squared. If you like, you can calculate angle alpha and figure out radius through H. So that's why I'll also put another variation for the omega, for the final omega, as square root of V over H squared. And instead of radius, I'll figure out through tangent alpha times H, right? So that means I'll get V squared over H and tan squared alpha. And as you understand, so right now I'm just can also simplify as V over H. And here what we'll get 1 plus 1 over tan squared. So we'll get square root of tan squared plus 1 becomes 1 over cos. So here we're just left with that one, tan squared alpha. If you want to express omega through radius, that's also be a variation in this case. It's going to be V over R and cos alpha finally, if we use the formula 1 plus tan squared alpha becomes 1 over cos alpha. There's also variation for that. So in each case you'll see your own solution. So that means we can use any of them. But because we are given H and L, I would prefer to use the first one. So that's the final formula here. All right, now we need to find angle theta. In which way we can do that? Tangent theta, let's write right here. So tangent theta is simply omega, let's see, it's omega 0 to omega 1, right? It's omega 0 to omega 1. And if you put that, it will be as 1 over tan alpha. Yes, omega 0 d over r, or basically cotangent alpha. Okay, so that's how we can define. Basically just take omega 0, take omega 1 and divide them. All right, so that's the final expression for the angle theta, and we can move to the second question, B. So in this question, we need to define magnitude of the angular acceleration of the cone. So as you remember, so angular acceleration alpha is simply d omega dt, where omega is the resultant vector that we defined on the previous stage. Okay, so because it's superposition, so we can differentiate omega 0 and omega 1 over time, over dt. Let's have a look. Because it moves uniformly, we will notice that omega 1 as the vector is not turning anywhere. Let's have a look at the picture one more time. So omega 1 stays on its place. So that means here's the omega 1 and it's constant. So that means derivative of that becomes 0. All right, and we need to differentiate d omega 0 over dt. So omega 0 is directed along OC in that way. So that's omega 0. So many students would say that derivative, because it's uniformly, so omega 0, so because the linear velocity of point C remains the same, so d omega over dt becomes 0. But it's not correct because it's vector, and vector change its direction, right? Over time it's turning. So we can use the Euler formula in that case. So basically what we have right now is omega 0 turning over the angle, let's say d theta, over time period dt. So that's omega 0. What it means that we can use Euler formula. So Euler formula. So Euler formula works in the way it would differentiate vector omega over time. So its direction vector will be turned. So let be direction vector as I. So we actually need to differentiate vector I. So that means, according to definition, it becomes the product of how vector I is turning with which angular velocity. So we need to actually apply that di dt and times in the vector way by omega 0, okay? Because omega 0 remains exactly constant in its magnitude. I'll put more proper letter, okay? So while di dt becomes actually omega 1, all right? So it becomes omega 1. So its magnitude, it's not unit vector, but I would say it's I times omega 1. So the magnitude becomes omega 1. That means, in our case, we will use the vector product for omega 1 and omega 0. But of course, because we need to define the magnitude of angular acceleration, so this is alpha, so we'll find out that it's simply omega 1, omega 0, and times sine of the angle. So alpha angular acceleration, its magnitude becomes omega 1, omega 0, and sine of the angle. But they are perpendicular, so sine of the angle becomes 1. And that means that's the final solution for part B. All right. If you like, you can express in the way alpha, so by plugging the parameters from omega 0 v over r, and for omega 1 we need to plug, where is the omega 1, v over h. So we've got v over h times v over r. And if you want to express r and h through the angle alpha, that also could take place. So we would use this relationship. R is h times tangent. So if you plug that, h times tangent alpha all the way back. So h we can express through radius. So radius over tangent alpha. In that case, we'll get something like that. V over r, tan alpha, and v over r becomes squared. So that's the final solution to our part B. Hope you like that. Don't forget to subscribe if you're new here, and see you next time.